Okay, in this example, we're told we have a stagnation tube placed in a supersonic flow. So let me just sketch that in here. So here's the stagnation tube. We have supersonic flow leading into it. And we're told that the static pressure and temperature far upstream are 60 kilopascals absolute. And the temperature is minus 20 degrees C. So we'll convert that over to an absolute temperature. So that would be 253 Kelvin. And the difference between the stagnation pressure measured by the stagnation tube, so that'll be P naught, and the upstream static pressure, so minus P, is 449 kilopascals. So the stagnation tube right here at this point right there measures the stagnation pressure. The reason is the flow is at a high speed here, and then it eventually comes to rest right at the entrance of the tube, and then we measure the pressure there. So that's why it's a stagnation pressure. Now we're asked to determine the upstream Mach number and the velocity of the flow. So we want to know the Mach number up here and the velocity of the flow up there. Okay, so first thing we need to recognize is that if the flow is supersonic, so we're told that the Mach number up here is greater than 1 because it's a supersonic flow. If it's supersonic flow here and it goes to a zero velocity here, then clearly we pass through a Mach number of 1 and then go subsonic and then reach zero velocity somewhere along the way here. Now, there are different ways you can go from supersonic flow to stagnation conditions. One way is to do it with a converging diverging nozzle, so something that kind of looks like this. Actually, let me change the shape a little bit. So it's be supersonic flow, you go through a throat, and then it goes subsonic, and then the area keeps increasing until you eventually go to zero. But clearly we don't have a throat in here, right? This is just some free stream. The other way you can do it is you go through a shock wave. So here's a Mach number greater than 1, you go through shock wave, it becomes subsonic, and then you can bring it to rest via it just comes to rest as it approaches the object here. Okay, so since there's no throat here, we must have some sort of shock wave upstream here. So when I write down, let me go ahead and erase this part here, but when I write down these pressures and temperatures, etc., and stagnation pressure, I'm going to put subscript 1 to indicate these are all upstream of the shock. And then this will be subscript 2 because it's downstream of the shock. Remember that upstream conditions are 1 and the downstream conditions are 2. So we're measuring the stagnation pressure downstream of the shock wave here. And this is the static pressure upstream of the shock. Okay, so in order to find this Mach number and velocity, the way I'm going to do that is the piece of information that connects what's happening across the shock wave is this piece of information, because this has some downstream, some upstream conditions. So I'm going to start there. And since I'm dealing with a shock wave, what I'm going to try to do is get this in a form where I'm dealing with the normal shock relation. So let me write it this way. So starting with P naught 2 minus P1, I can write that, for example, as P1 times P naught 2 over P1 minus 1. And then I can take that ratio P naught 2 over P1 and write it as P naught 2 over P naught 1 times P naught 1 over P1. And again, the reason I did this was I wanted to get it in terms of these ratios that we're used to using in with compressible flows. So this one, for example, I could get from the normal shock relations, and this one I could get from the isentropic relations. This is given, right? And if I when I say the normal shock relations, remember those are a function of the upstream Mach number, and the isentropic relations are also a function of the Mach number. And since these are all subscript 1 here, it's all a function of this upstream Mach number. So this whole right-hand side now is a function of the upstream Mach number, right? So we can work with that kind of expression, right? So I can go ahead and write, for example, P naught 2 over P naught 1. Let's see if I have that. That's a long expression. I'm just going to write it as function of Mach number 1. If you go back to the formula sheet, and so let me quickly find the formula sheet, you'll see that that expression is given right here, P02 over P01. It's all a function of the Mach number upstream. And then the other one was P1 over P01, and that one is right here. It's just flipped upside down here. Okay, so those are the expressions I'm going to be using. Okay, so that's what I mean when I've written this here. It's just those expressions from the formula sheet here. Those expressions were derived in a lecture. So you'll see this whole thing is now a function of the upstream Mach number times P1. Right? Let me write that a little differently. Right? So I've just written this as that. Okay, so now that we have that, you'll see that we now have an equation, right? So the P02 minus P1, that was the 449 kilopascals. And that's equal to P1, which we know is 60 kilopascals. And then the function of Mach number 1, well, that's what we're trying to solve for, is Mach number 1. This is a complicated expression, right? When you combine these together, it's a complicated expression. You're not just going to get an equation where it says Mach number 1 is equal to something and then solve it, right? That's not going to happen. It's a much more complicated equation. So we have to solve it numerically, and there are various methods for doing that. My suggestion is just to use a root finding method, for example, like a bracketing method or Newton-Raphson method, something along those lines to solve for what the Mach number is upstream. So I won't give the details of that, but I'll just say down here, using a numerical root finding method or algorithm, we can solve for the upstream Mach number, and you'll find that it comes out to be about 2.49. Okay. So to find that, just to recap very quickly, the way we did that is we recognize that there has to be a shock wave separating the upstream supersonic flow and the stagnation conditions here because there's no throat in between. And then we wrote the P02 minus P1 because that's what connects the information across the shock wave in terms of some ratios that involve the upstream Mach number. So that's this part right here. You can see that like the P01 cancels out there. Okay, and we recognize that these ratios involve the upstream Mach number in a complicated way, but nevertheless we have an equation where we know all the numbers and the only unknown is the Mach number upstream, and we use a root finding method to find that to arrive at this point. By the way, the root finding method, one that I recommend is just using the root finding methods within Python. There's a library called SciPy that has root finding methods there. Okay, the next part of the problem is to find the velocity upstream. That part is pretty straightforward. We know the Mach number upstream is just the velocity upstream divided by the speed of sound upstream, where the speed of sound is the square root of kr times the temperature upstream, T1. And we know all of this information. We know K, we know R, we know T1. That's the 253 Kelvin. So we can solve for that speed of sound. We now know the Mach number upstream, so we can then solve for the velocity upstream. So if you go through that effort, you'll find that the velocity comes out to be 795 meters per second. Okay, I think that's everything we need for this problem, so we'll just go ahead and end it there.